Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 9, Section 5 notes over the laws governing how compounds form. So we're going to be talking about two laws, and they are the laws of definite and multiple proportions. The compound calcium carbonate, CaCO3, contains three elements: calcium, carbon, and oxygen, combined in the same proportion in every molecule of CaCO3. So in every molecule of calcium carbonate, they are in the same proportions. There's two laws: the law of definite proportions and the law of multiple proportions, and they describe the proportions in which elements combine to form compounds. Let's start off with the law of definite proportions. A chemical formula tells us, by means of subscripts, the ratio of atoms of each element in the compound. Ratios of atoms can also be expressed as ratios of masses. For example, if you took 100 grams of magnesium sulfide and you broke it down into its two elements, you would obtain 43.13 grams of magnesium and 56.87 grams of sulfur. Now we can figure that out just by looking at magnesium and sulfur and figuring out what percent each of those atoms takes up and multiplying it by 100, and that's how they got 43.13 and 56.87 grams. So the Mg to S ratio of these masses is 43.13 to 56.87, or 0.758 to 1. This ratio never changes. Magnesium sulfide obeys the law of definite proportions, which states that in samples of any chemical compound, the masses of the elements are always in the same proportions. The law of definite proportions is consistent with Dalton's atomic theory, because Dalton postulated that atoms combine in simple whole number ratios. If the ratio of atoms of each element in a compound is fixed, then it follows that the ratio of their masses is also fixed. Now let's talk about the law of multiple proportions. In the early 1800s, Dalton and others studied pairs of compounds that contain the same elements but have different physical and chemical properties. Using the results from these studies, Dalton stated the law of multiple proportions as follows. Whenever the same two elements form more than one compound, the different masses of one element that combine with the same mass of the other element are in a ratio of small whole numbers. So basically what that is saying is that there are different compounds that are composed of the same elements. So if we think about carbon monoxide and carbon dioxide, that's CO and CO2. Those are two completely different compounds. They have completely different properties, but they're composed of carbon and oxygen, but just in different ratios or proportions. The figure on the right demonstrates the law of multiple proportions. Copper 1 chloride is green at the top there, and copper 2 chloride contains the same elements, but this compound is blue. Another example is water and hydrogen peroxide, so that's H2 and H2O2. And H2O2, it would kill you if you drank it, and it also bleaches dyes, whereas water, composed of the same elements but a different ratio, we need water to live. We need that to survive. Both of them, water and hydrogen peroxide, they obey the law of definite proportions. In every sample of hydrogen peroxide, there is 16 grams of oxygen are present for each 1 gram of hydrogen. The mass ratio of oxygen to hydrogen is always 16 to 1. In every sample of water, the mass ratio of oxygen to hydrogen is always 8 to 1. If a sample of hydrogen peroxide has the same mass of hydrogen as a sample of water, the ratio of the mass of oxygen in the two compounds is exactly 2 to 1. So if we look at this, we have 16 grams of oxygen, and that's in a sample of hydrogen peroxide that has 1 gram. And there is 8 grams of oxygen in a sample of water that we say has 1 gram of hydrogen. So we divide that out and we get 16 over 8. We round those down. Smallest whole number ratio, 2 to 1. So hydrogen peroxide has twice the amount of oxygen as water does. Now let's talk about calculating mass ratios. Carbon reacts with oxygen to form two compounds. Compound A contains 2.41 grams of carbon for each 3.2 grams of oxygen. Compound B contains 6.71 grams of carbon for each 17.9 grams of oxygen. What is the lowest whole number mass ratio of carbon that combines with a given mass of oxygen? So the first thing we want to do here is we want to list our unknowns and our knowns. So we're going to list our knowns. And our knowns, we know that compound A, I'm going to abbreviate that to CMPD-A, has 2.41 grams of carbon and 3.22 grams of oxygen. Whereas compound B has 6.71 grams of carbon and 17.9 grams of oxygen. And our unknown, what we're trying to solve for is the mass ratio of carbon per gram of oxygen in the two compounds. Now I know this seems a little confusing right now. It is a confusing topic, but as we get more practice with it, you'll see that the math is pretty simple and that it ends up being a fairly simple concept to understand. So our next step is to use our known amounts of carbon because we want to calculate the grams of carbon per 1 gram of oxygen in compound A. So to do that, we just are going to be using ratios. So we're going to say that 2.41 grams of carbon for 3.22 grams of oxygen, which is just from our knowns. And what we're trying to do is solve for grams of carbon per 1 gram of oxygen. So when we end up solving that out, we get 0.748 grams of carbon per 1 gram of oxygen for compound A. Now for compound B, we're going to do the same thing. So 6.71 grams of carbon for 17.9 grams of O. Same thing, we're going to call this one X2. We want to figure out how many grams of carbon are present in compound B for every 1 gram of oxygen. So when we do the math here, we get 0.375 grams of carbon and so then our last piece is 0.748 grams over 0.375 grams, which comes out to be 1.99 or roughly 2. So what this tells us is that our mass ratio of carbon per 1 gram of oxygen is 2 to 1. Now, like I said, I understand this is pretty confusing. It's even a little confusing for me whenever I had to look back over this stuff. But once we get practice with it tomorrow, we're going to figure it all out. So let's talk about, does this result make sense? And it does make sense because we have a small whole number ratio. The ratio is a low whole number ratio, like I said, as expected. For a given mass of oxygen, compound A contains twice the mass of carbon as compound B. All right, now we're going to be going back over some reviews to end the chapter. So this is our major key alert. DJ Khaled would be pretty excited with us. So our first key is that if the compound is binary, generally the name ends with the suffix IDE. If the compound is a molecular binary compound, you're going to use prefixes to indicate the number of atoms. When a polyatomic ion that includes oxygen is in the formula, the compound name generally ends in ITE or ATE. If the compound contains a metallic cation, that can have a different ionic charge, use a Roman numeral to indicate the numerical value of the ionic charge in the compound. So if you look at this flowchart here, we're going to talk a lot about this in class as we continue through. Once we start looking at worksheets that are going to have acids, bases, ionic compounds, with polyatomic ions, with binary ionic compounds, and moleculars all mixed together, this chart is going to help us out. And it's in your book. I recommend copying it down so you can use it as we progress forward. An IDE ending generally indicates a binary compound. An ITE or ATE ending means a polyatomic ion that includes oxygen is in the formula. Prefixes in a name generally indicate that the compound is molecular. A Roman numeral after the name of a cation shows the ionic charge of the cation. And again, here is another flowchart. This is when you have the name and you're trying to go to the formula. So some more keys. If the ratio of atoms of each element in a compound is fixed, then the ratio of their masses is also fixed. An IDE ending usually indicates a binary compound. An ITE or ATE ending indicates a polyatomic ion with oxygen. Prefixes, again, usually indicate our molecular compounds. Roman numerals after the name of a cation shows the ionic charge of the cation. And that's going to be it for our Chapter 9, Section 5 notes. And as always, the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, Resources CD, and pearsonchem.com. Thank you, and have a good rest of your day.